What's up, guys? Okay, I'm going to go over this worksheet with you. Starting with sodium. Sodium on the periodic table has one valence electron. So quickly, I'm going to pick a pen first and then draw sodium Na with one valence electron. There we go. Easy. Silicon, four valence electrons on the periodic table. So silicon, Si, 1, 2, 3, and 4. Don't forget to spread out the electrons. We don't pair unless we go around the second time, then you can start pairing them off. But in the case of silicon, because there's only 4 and there's only 4 sides, we have 1 electron per side. And that is how you draw the Lewis diagram for silicon. Chlorine. Cl has 7, so 1, 2, 3, 4, and now you can pair 5, 6, 7. That's chlorine. All right, now let's get to something more interesting, which is actually writing out the compounds. So barium sulfide. So remember, you need to figure out whether these are covalent or ionic compounds. So if we have an ionic compound, we would use the charges. We'd show the charges and we'd show square brackets because that's how ionic compounds work. It's a transfer of electrons resulting in two oppositely charged atoms, which we call ions, and then those are attracted to each other. Whereas if it's covalently bonded, a covalent compound, the electrons are shared, and we would draw lines between them. Okay? So how do you figure out whether this is ionic or covalent? Look at the two elements that you have here, barium and sulfide. Barium happens to be a metal, number 56 on the periodic table. Sulfide is sulfur, which is number 16 on the periodic table. So we have a metal with a non-metal. And because we have a metal with a non-metal, this must be ionically bonded. So we're going to use the charges in order to draw the Lewis diagram. But first of all, we need to know the ratio of the two ions. So how would you balance barium and sulfide? Well, Ba2 plus, S2 minus, that results in BaS. Okay? So 1-to-1 ratio. So if it's a 1-to-1 ratio, then we're going to put square brackets. Barium's going to lose its 2 valence electrons. So we put 2 plus, and we don't draw any electrons on barium because it's lost the 2. And now we're going to draw sulfide in square brackets. But for sulfide, we have 6 valence electrons plus the 2 that barium gave it, which is 8. So we have 8 electrons around the sulfide ion. And the sulfide ion has a charge of 2 minus. So that is the Lewis structure for barium sulfide. Magnesium chloride. Magnesium is metal, chloride is a nonmetal. This is ionically bonded. Let's figure out the ratio. So magnesium is 2 plus and Cl is 1 minus. So it must be MgCl2 in order to be balanced, because you need 2 of the Cl minuses to balance out 1 of the Mg2 plus. And so that compound exists in the ratio of 1-to-2. So for magnesium, we draw it like this. Again, no electrons around the Mg because it's going to give up 2 electrons. So it's not going to have the 2 electrons anymore. Chlorine, because there are 2 chlorides, we put a 2 coefficient outside, and then Cl and then 8 electrons around it. There's 8 because chlorine normally has 7, and then it's given 1 electron by magnesium, and then the other chlorine's given the other electron. So each chlorine adds 1 more electron to it from the magnesium, and there are 2 chlorines, so that balances out. Carbon dioxide. Carbon dioxide is a covalently bonded compound. It's a molecule, and you should know that. So we have carbon and oxygen. Those are both nonmetals, so it's got to be covalently bonded. So how do you do this? Well, what you do is you take a look at the valence electrons. Carbon has 4, and oxygen has 6, but there are 2 of them. So how many is that? 2 times 6 is 12, plus 4 is 16. So there should be 16 electrons shared between carbon and oxygen. So I'm going to start off with carbon. Let me just move this C over a bit. Let's put it in the middle, just in case we need more space. It's carbon dioxide. So carbon's going to go in the middle. And there's 2 oxygens. I'm going to put them to either side of carbon just to spread it out. Okay, and then let's take a look at whatever's left over in terms of electrons for carbon. Okay, so we have carbon has 4 valence electrons, so 1, 2, 3, 4. And then if it's sharing 4 electrons, then it's 1, 2, 3, 4, 5, 6. That does not follow the octet rule. The octet rule states that each atom in a covalently bonded compound has to have 8 electrons around it. Okay, so carbon only has 6, so that doesn't quite work out. So let's try this. What if we took these 2 electrons that are at the top here and at the bottom and formed bonds with oxygen? So there's a double bond. Well, then you'll have 1, 2, 3, 4, 5, 6, 7, 8. So that's perfect for carbon. Let's check out oxygen now. Oxygen has 6 valence electrons, so it's already got 2 in bonds. So that leaves 4. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So it's got 4 in the bond with carbon and then 4 left over. So that's 8. So the other oxygen must be exactly the same, like this. Okay, so this should be what carbon dioxide looks like. Carbon with double bonds with each oxygen. Okay, and then there's 4 lone pair of electrons around the oxygens. Table salt. You should know that table salt is NaCl, perfectly balanced like this, 1 of each, and Na has a charge of +1, Cl has a charge of -1, done. Lithium oxide. Okay, so lithium oxide, lithium is a metal. Oxide is a non-metal, so this is ionically bonded. Lithium oxide, if you balance it out, lithium is +1, oxygen is -2, so it should be Li2O. Okay, and if you don't know how to do that, please go and review the grade 9 stuff that I posted in the form of videos to remind yourself how to balance these ions. So lithium, Li, all the electrons are taken away by oxygen, and it's got a +1 charge. Oh, sorry, we should have 2 lithiums, so I put a 2 coefficient on the outside. And then for the oxygen, there's 1 oxygen, And it should have 8 electrons around it because each lithium has donated 1 electron. So that adds up to 8. So now we have oxygen with a 2 minus charge because it got 2 electrons from each lithium. And so there's your Lewis diagram for lithium oxide. Carbon monoxide, again, it's named with a mono, Greek prefix. So that means that we have a covalently bonded compound. Carbon monoxide, C and O. 1 oxygen, 1 carbon. So let's see how we can work this out so that we have the octet rule satisfied. So normally carbon has 4 valence electrons. So let me just write up here 4. And then oxygen has 6 valence electrons. So that equals 10 valence electrons. Okay, so 10 electrons must be shared between these 2 atoms. Let's see how we can make this work and also satisfy the octet rule. It has to satisfy the octet rule, which is to say each atom should have 8 electrons. Currently, carbon has 1, 2, 3, 4, 5. Well, this is no good. So what if we took one of these electrons? How do I get my eraser? Take one of these electrons and then let's make a double bond. Okay, so now we've got 1, 2, 3, 4, 5, 6. Still no good. Let's do this again. Eraser doesn't work. There we go. And let's take that 1 electron and make a double bond. Now we have a triple bond. So let's count these again. 1, 2, 3, 4, 5, 6, 7. Well, that's not going to work. So what are we going to do? Let's take a look at oxygen. Oxygen has 6 valence electrons. So if it's got 6 valence electrons, 1, 2, 3, 4, 5, 6. How are we going to do this? Oxygen is not going well here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. It shouldn't have 9 electrons surrounding it. We're going to have to get rid of 1. So the only solution to this, it seems, is to get rid of this electron beside oxygen here and put it on the other side with carbon, which you can do because all these electrons are flying around these 2 atoms, so they're all shared. And let's just pair it up with this carbon here. Does this work? Look at carbon. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule. Okay, so both of these satisfy the octet rule, and so this is what it looks like for the Lewis diagram. Okay, so that's carbon monoxide. Let's take a look at the next page. On the next page, we've got water. So for water, H2O, and you probably have seen this before, you're going to have oxygen in the center with 2 hydrogens. And it makes this kind of shape, so we might as well put it in that shape because you know that already. Now later on in chemistry, the shapes do matter, but for chemistry in grade 10, not a big deal. Let's just do this for water because we know water is like a Mickey Mouse shape. Okay, so oxygen has 6 valence electrons, and if you count it up, it follows the octet rule, so we're good. Next one, H2S. Here's another covalent compound. So I'm going to stick S in the middle as the central atom. And I'm going to join this up with H and H on the other side. So let's see. We've got sulfur. Sulfur has 6 valence electrons. So 1, 2, 3, 4, 5, 6, and then 7, 8. So that follows the octet rule. And for hydrogen, the octet rule also is satisfied because hydrogen should only have 2 electrons that are shared around it. SiS2. So let's put Si in the middle, and let's put one S on each side, like this. So that's how we're going to start off. And so we've got silicon, which has 4 valence electrons, plus 2 sulfurs. Each sulfur has 6. So 16. So let's take a look at the silicon in the middle. Silicon should have 4. So we've got 1, 2, 3, 4, 5, 6. That doesn't quite work. So let's see what we can do about this. Let's try moving these 2 electrons and forming double bonds with sulfur and see if it satisfies the octet rule. So 1, 2, 3, 4, 5, 6, 7, 8. That satisfies the octet rule. Now let's look at sulfur, the 2 sulfurs. Sulfur has 6 valence electrons, so that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So each of these sulfurs has 1, 2, 3, 4, 5, 6, 7, 8. This sulfur is 1, 2, 3, 4, 5, 6, 7, 8. So everything follows the octet rule. And if you count it all up, you should have 16 electrons in total shared. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. Okay, let's take a look at this molecule. So we have quite often with these organic compounds, carbon is going to be central. So carbon is bonded to 2 hydrogens, it looks like, and 2 bromides. Okay, so 2 bromines are linked to this carbon as well as 2 hydrogens. So carbon has 4 valence electrons. It already satisfies the octet rule here because 4 times 2 is 8. Hydrogens are satisfied. Let's look at the bromines. Okay, so it's got 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, and 1 more that's shared. That makes 8. So that's perfect. So these satisfy the octet rule. That's how it should look then. HCN. So carbon with nitrogen with a hydrogen. Okay, hydrogen usually only has 1 bond to it. Carbon has 4 valence electrons. In this case, the octet rule is not satisfied. So what we're going to do, because we have 1, 2, 3, 4, 5, 6, what we're going to do is we're going to take one of these electrons and let's make a double bond with nitrogen. So 1, 2, 3, 4, 5, 6, 7. That's still not satisfying the octet rule. So I'm going to take this final electron and put it on the right side to make a triple bond with nitrogen. Why don't I put it with the hydrogen? Well, think about it. Hydrogen only has, in the first place, only has one electron flying around it. So there is no other electrons for it to make any more bonds with. So hydrogen always only has a single bond with whatever it's bonding to. So in this case, if we have a triple bond with nitrogen, for hydrogen, the octet rule is satisfied already with 2. Carbon, 1, 2, 3, 4, 5, 6, 7, 8, satisfied. Now let's work on nitrogen and make sure nitrogen has the correct number of electrons around it. It's got 5 valence electrons. So 1, 2, 3, 4, 5. Okay, it's always good to check to make sure that it's the correct number of electrons overall, and everything satisfies the octet rule. For nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is satisfied for all 3 of these. Double check the number of electrons in total. So hydrogen has 1, and then carbon has 4, and then nitrogen has 5. So that equals 10. If you count them all up, there should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. 10 electrons that are shared. Each atom satisfies the octet rule, so this should be the Lewis structure for HCN. Ammonia, our good friend ammonia. Nitrogen with 3 hydrogens. So right away, I'm going to draw bonds to each of these hydrogens. Okay. And for nitrogen, nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. Does it satisfy the octet rule? Well, 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. So we'll leave it. That's what ammonia looks like. C2H4. Okay, so once again, carbon should be at the center of this, and there's 2 carbons, so we're going to put them together like this, and then 4 hydrogens. So I'm just going to draw it like this. So it seems like we're missing electrons from carbon because carbon's got 4 valence electrons, so we're missing 1 from each. So if we're missing 1 from each, they can just form a bond like this. Let's see if it follows the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And of course it should be exactly the same for the other carbon. All the hydrogens are satisfied. We should have a total of 2 times 4 is 8, plus 4 times 1 is 4. 12 electrons in total if you count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. NaCl. We've done so many covalent compounds. Don't get mixed up here. Even though we're doing lots of covalent compounds, I'm also just always double checking to make sure I'm not stumbling and making a mistake and doing covalent bonds for ionic compounds. Sodium chloride is salt, so we're just going to go Na plus and Cl minus. That's table salt. Mg3N2. Looks like this last one is also an ionic compound. So it's already, the ratios are already given. So we're going to have 3 magnesiums. Each magnesium has a 2+ charge. And then 2 nitrogens. Each nitrogen should have 8 electrons around it because it's taken 2 from magnesium. It originally had 5. So it's taken 2 from each magnesium. So that's Oh, yes, so each nitrogen should take 3 electrons. It's because it's got a 3 minus charge. So 5 plus 3 gives you the 8 electrons around nitrogen. There's 2 of them, and there's 3 magnesiums. So this should be the Lewis structure for that one. All right, that's it. Till next time.